So let's look at this discussion problem here. This is going to be a static equilibrium problem. So we have one end of a uniform meter stick of mass 0.25 kilograms is placed against a vertical wall. The other end is held by a lightweight cord making an angle of 20 degrees with the stick. So let's start kind of populating our picture. So this is our angle here, angle theta of 20 degrees. A block with the same mass as the meter stick is suspended from the stick a distance of 0.75 meters from the wall. Find the tension in the cord and the frictional force between the stick and the wall. So as usual, let's look at the forces that are acting on this meter stick. So if I go through, so here's the first force, is the tension, and it's going to again acting up that rope just like usual. Having trouble drawing this, but this is the idea. So this is the tension. Over here on the rope, I'm going to have a force, and I'm just going to call this mg since the masses are the same. That's nice. Acting over here where this block is hanging. There'll be another mg hanging right in the middle of the stick, right? And so for this one, this distance, I'll just call the length of the stick L, and so this one will be acting at a length L divided by 2. And in the problem, we're told that this one's acting at a length 3/4 L, just to kind of make sure we have our picture set. And then finally, here at the wall, and so it's going to be tough to kind of draw this, so it's acting right here at the wall. There'll be the frictional force upwards, that I'll call just F. This will be static friction. And then there'll be the normal force of the wall pressing against the stick there. And again, when we're doing problems like this where there's something put up against a wall, they can do it, they have different kind of connections there, but unless it's really clear in the problem that there's only one force, it's just a good rule of thumb to assume that there's two forces. And here, we're not told to neglect friction. In fact, we're asked to find it. So there is a friction going parallel to the surface, and then just like usual, a normal force pressing perpendicular to the surface. And so those are our 5 forces. So 2 mg's, the tension, and then the friction and the normal force. All right, so what are we doing here? So again, we sort of drew our free body diagram. We're kind of ready to attack this problem. It says we want to find the tension in the cord and the frictional force between the stick and the wall. So let's start by doing the frictional force. And so to do that, I'm going to do a torque positive equals a torque negative equation. And so I invite you guys to pause this and give this a go. So try to find the place that might be the best axis. So again, here we're trying to find the tension. So sort of find the best axis of rotation to pick, because again, we have the freedom to pick our own axis of rotation here to find the tension, and then try to go ahead and do it. And we'll talk about this in a second here. Okay, so hopefully you got that the best axis of rotation to find the tension will be right here. And why is that? Well, that basically gets rid of the force of static friction, because that could be applying a torque. And so if I make the axis right there, then both the static and the normal force can't be applying any torque about that axis, and so it makes our life easier. We kind of get rid of those two forces. And so the force that we're going to have there will be the tension, and then the 2 mg's. And so if you look here, so this tension would be like this. And so what I'm going to do is again, there's a couple different ways to do this, but I think what I'm going to do here is just say to myself, I know that with this tension, I can break it down so that there's sort of a component of the tension pulling up, and I'll try to make this, switch this T over. There's a part of the tension that kind of, I'm sorry, I cannot get this straight somehow. That's close enough. And so this, I would call this T sine of theta. That's the part that we would call our y direction, and then there will be another component, T cosine theta. I'm trying to draw these so that we can tell that they're both acting right at this point, which is important. But basically, it's just taking that tension and break it into its two components. So make sure that that makes sense. And then when you do that, hopefully you can see that the one doing the twisting will be the tension sine of theta. The tension cosine is just basically pushing the meter stick onto its axis and can't do any twisting. And so here, I'm going to call this T sine of theta, and then I just put L for the total length of the stick is the moment arm, right? So we can be a little bit more precise about this. But if I was to draw the line of action through here, then the shortest distance between the axis and my force is this right here. And so it's going to be the moment arm of L. And so this is our positive torque, right? That's the one that makes it want to go counterclockwise. And then there's the two mg's, and so let's do the one halfway out. So for the one halfway out, its moment arm is going to be that L divided by 2. So that's the mass of the stick. And then we'll have mg for that hanging box. Again, they were nice to us in this problem. They made them the same, and the moment arm in that case would be 3/4 L. And so now we're basically ready to go through and solve this. And so the L is 1 meter, but at the same time, since it's in all of these, I can just sort of cancel it out. And so then I can isolate the tension by saying mg divided by 2 plus 3/4 mg divided by this factor of sine, which will come out to be sine of 20 degrees. So again, this is 3/4, 1/2, and then as we're told in the problem, the mass is 0.25 kilograms. When I plugged in these numbers, I got a total tension of 8.95 newtons. Okay, so that's the first part. And so generally with these problems, again, they're always a little bit different, but I think you can sort of do the torque and get something there. So we did that. We did the torque, we got the tension, and then now it's usually easier to kind of backtrack and then just use forces for this sort of next picture. And so let's go over to here. And so let's see, maybe good just to kind of draw our picture setup again, because it got a little bit busy that last time. And so here's my tension. Again, here's a force of mg. There's a force of mg acting there. And then here on the wall, and now again, you could ask yourself, how do I know the static friction goes up? This is the case where I just sort of guessed. And you'll be told in the problem, you'll get a negative answer if you were in fact wrong. And then a normal force pressing that way. And the one last thing that I'll do is just remember that here we can replace this tension with sort of two forces, if you remember. There's the tension sine of theta, and then the tension cosine of theta. So we did that, and it'll help us here too to have that broken down into its components. And so I'll just do the sum of the forces in the y direction equals 0. So we're actually told to try to find the frictional force, and so to do that, I'm going to use my y information. We'll use our typical xy axis, kind of looking like this here. That's the y, and that's the x. And so if I add up my forces, I'll have a positive frictional force, a positive. Now here's important. It's only the t sine of theta that's in the y direction, right? So you got to be real careful to isolate that. So that's t sine of theta, and then minus the 1 mg for the stick maybe, and then minus mg for that block hanging there. And so that would be my equation. Again, these are two upwards forces, these are two downward forces. And so now if I solve for that static friction, I'll get a total of 2 mg minus t sine, again that theta is 20, and then t, we just solved for t, right, over here, we got 8.95, so I'll put 8.95 newtons, and then again the mass is 0.25 kilograms, and so when I calculated this, I got a positive 1.83 newtons. So that means I guessed the direction of the static friction correctly. Again, it's not a super big deal, because if you didn't guess it, it would just be sort of downwards. And so, like, if you say, well, how can I get a little bit more insight into this? Again, what you could do is, like, imagine if we had picked our axis to be over here, right, where the tensions are, and then you've got these, from that perspective, the mg's are doing a positive torque downwards, and so from that picture you can kind of see that, well, the static friction would have to kind of go this way to balance out those torques, right? So if you imagine then the axis being on the other side. But again, it's not super crucial. You can just kind of guess too at this point. And then the problem didn't ask you to do this, but why not just complete it and find the sum of the forces in the x direction. And so again, by my positive side, I'd have force normal minus t cosine 20, because that's again acting sort of in the backwards direction, so cosine of the theta equals 0, and so then my normal force equals tension cosine of 20. Again, my tension was 8.95, and so when I did this one, I got 8.41 newtons. Sometimes they'll ask for both. This one didn't, but it's just kind of nice to complete there. So a static equilibrium problem, and definitely with that tension going at an angle. This is a common one. You'll see this problem often. All right, hope this helped.